we're going to talk about Verilog. However, we're going to talk about Verilog for synthesis and only for synthesis. The goal of going through Verilog design and the Verilog language here is purely to understand what Verilog can do to implement an actual circuit that can be manufactured. We're not going to talk about all the aspects of Verilog used for simulation and non-synthesizable keywords. Indeed, Verilog has a split personality. Verilog is a hardware description language. It is used to be reliable and to be readable, to create hardware and to document hardware. It is also used as a test bench creation language to create external test environments for the hardware description language block that you have implemented. As such, it supports the notion of time and voltage, files and messages, and so on and so forth. However, are these two tasks related and compatible? Related, definitely. You need to have a test bench in order to evaluate a circuit. That seems pretty standard. You want to emulate what's going to happen on your design under test. However, is that compatible? Well, if I'm telling you, please wait for 10 nanoseconds, well, you will understand that kind of statement because you know what time is. However, is a clocked digital circuit knowing what time is? No. For this circuit, time is only coming through the clock. The only thing your digital design knows is how to react when there has been a new rising edge on your clock. As such, these two different goals in the Verilog language are very much incompatible. To go through a quick review of the Verilog language, let's first have generally how a module is organized. So modules are going with the syntax. So you start with a module keyword, providing a name and providing arguments, and you open the begin keyword. You will finish your module with the end module statement. At the very beginning of your begin module, you will have the definition of parameters, definition of inputs, outputs, wires, registers. And from there, you will be able to have the main part of the module that's going to be executed concurrently with continuous assignments and always blocks. I'd like already now to mention that it goes without saying, you already know that since you are familiar with Verilog. Verilog should not be used to write a piece of code as a software designer would do. You're using Verilog to describe a hardware element. And as such, you need to know what your circuit is supposed to do, you need to have a block diagram written, and you need to understand that all your various blocks are going to work and being evaluated concurrently. It is not sequential as a regular C program would be. So let's continue our quick review. We can do continuous assignments to wire variables using the following syntax. Assign a variable equal to something. This results in combinational logic. Indeed, this something could be a complete logic expression combining several types of information. For the procedural assignments, they are assigned to register variables. A register variable is a flip-flop, right, or a complete register, and therefore it is going to be having a notion of time, right? That's when you latch your flip-flop, when you trigger your flip-flop. And as such, you create this assign statement, this always statement that will contain the information used to evaluate what is happening when I am actually triggering the sensitivity list of my process. So all the procedural assignments are using an always block for synthesis, and inside of this always block, you will find two types of operations. Either blocking assignments with the syntax variable equal to the expression, or non-blocking assignments, variable lower than equal to expression, or arrow expression. A procedural assignment can result in combinational or sequential logic depending on how you write your Verilog. The difference between blocking and non-blocking would mean that when your synthesizer or when your simulator is evaluating these procedural assignments, you will have to understand if you have to read that sequentially, in this case as a piece of software, or if you can evaluate that in parallel at the same time. That's the difference between blocking, I do one after the other, or non-blocking, I do all of them at the same time. Verilog can have different description styles. A description style is the way you write your Verilog code in order to support various needs. The first one is a so-called structural description, where you give an explicit structure of the circuit. It resembles very much a netlist, where each logic gate is instantiated and connected to others. You will have, for example, a NOT gate and an AND gate, and they're connected together. This is structural. The other option is to have a behavioral description, where you are going to describe the behavior of your circuit between the input and the output. And many structural implementations could have the same behavior. For example, if I write in my Verilog, y is equal to a plus b. A plus b is a behavioral description. I am performing an addition between the vector a and vector b, but I'm not providing details on how this addition should be done. Is that going to be a ripple carry adder? Is that going to be a carry look-ahead adder? The synthesizer will decide for you. If you wanted to explicitly have a ripple carry adder, you would have to describe the structure that you want in structural Verilog. Now, during synthesis, and in your Verilog code, you can use several data types. We did talk about the wire and registers variables. Those registers and wires can take the following possible values. It can be 0, logic state 0, meaning false, or logic state 1, meaning true. It can be high impedance, Z, meaning that the gate is effectively not assigning anything on this wire or register. Or it could be unknown. Unknown because you don't know the initial state of your system, or unknown because you have a potential conflict. In digital hardware, which is the domain of Verilog, we are implementing either logic through logic gates or storage through registers and latches. And as a result, Verilog has two relevant data types, which are wires, like a regular wire in your circuit, that does not store information, just propagates information, and registers that will actually contain the information at a given time and maintain the value. How can I declare those different data types? Well, you can declare a register having a simple expression like reg A, which implements a scalar register, or you can have an array of registers, which in that case, reg 320B means that B is a 4-bit vector register. Note that an output can actually be a register, and you can declare your output G followed by reg G. That way we know that G is an output and G is a register, so your actual register is connected straight to the output. But you could also combine these two functions as output reg G on a single line since the introduction of Verilog 2001. Wires are very much so defined, where you have wire D to implement a scalar wire, wire 320E to implement a 4-bit vector wire, and if you have output F, your output F would be a wire. Note that in that case, you do not need to declare the wire to be F. You only want to declare that specific variable to be a register if you want your output to be a register. Otherwise, by default, it will be a wire. In addition to declaring data types that way, you can also use parameters that are used to define constants. For example, you can use parameter size equal to 16 or foo equal to 8, and define the size of your wire bus by using the following syntax. Wire, between brackets, size -1, column 0, will create an actual 16-bit bus because the parameter size has been set to 16 in that case.